Okay, this is robot motion planning chapter. In this chapter, we will work on some primitive algorithms for making such robots, field robots or point robots, any kind of robots, autonomous. And you will see that we are only trying to avoid collisions with the obstacles in the environment. And we will be focusing on 2D environments, but the same approaches may be also employed in 3D environment. But the thing is that you need to have a bit variation of these algorithms. So in this robot motion planning, the main goal is to design such autonomous robots so that if you have proper algorithms, they will decide on the path themselves, and without any human intervention, they will be able to start from a defined point and then reach to the goal point. And if that's the case, then we can name such robots as autonomous robots. And during their motion, they should be colliding with any kind of objects in the environment. So obstacles are highly important. The robots should be able to actually somehow detect such obstacles, or you may define them in advance with different data structures. So it's up to you, up to your design, up to your approach. And we can also apply such kind of algorithms not only on the field robots or moving such kind of things like cars, trucks. We can also employ such algorithms on also industrial robots. They can, for instance, perform pick and place tasks. They can perform welding operation and other assembly operations. So you need to define some algorithms or add some specific sensors so that your robot will always be detecting any obstacles in the environment, and then while it's doing its task, while accomplishing its task, it shouldn't be colliding with any other things, humans in the environment, robots, any moving obstacles. So with the help of these sensors, they will try to avoid such collisions. So these are the things the robot actually should know about the environment, be able to detect the obstacles, and move their, let's say, end effector. If it's an industrial robot, move their end effector from the specific starting point to the goal position. And as I mentioned, we will be working on 2D problems, and in our 2D environment, all the obstacles and the robots will be polygonal. They may have 3 edges, 4 edges, 5 edges, doesn't matter, but they will be all polygonal. And another issue is that just the robot is moving, the other things in the environment are all stationary, and that's why we name the environment as a static one. If they are moving, then the problem will be highly complicated. You need to have powerful sensors to determine the motion of other obstacles and then update your path accordingly. And the robots can make actually different motions. They have the various types of motions, and this depends obviously on the mechanics of the robot. It may only be moving, for instance, in one direction, in just X, or another one might be just rotating. And another one might have just an X motion and rotation. So that might be quite enough to reach the endpoint on 2D plane. But we will see that in our example, we will have 2 translational motions and 1 rotational motion. So before you start the problem, you need to be aware of the mechanics of your robot or robots in the environment. But if you are, as I mentioned, if you have some obstacles moving dynamically in the environment, if you consider, for instance, the cars moving in the streets, we have other cars, people moving all around, so the problem is highly complicated. You need to, another complication actually comes from the complicated mechanics of our cars, their motions, their relations, mathematical relations should also be included in your path determination. And to make things simpler in this chapter, we will assume that our robots are only doing translational motions first, and then we will add another degree of freedom to our robots. Here's an example, a simple one. This is our environment. We have some polygonal obstacles. This is our robot, another polygon. This is a starting point. By following a path, it goes to a final point. And this one has no rotational capability. It's just moving in X and Y direction. So this one moves, for instance, in Y first and then in X without rotating, and then goes in Y, X, Y, and X to reach the final position. Any questions, guys, about these introduction, these terms? We will jump to a bit different topic now. It's about workspace and configuration space. In robot motion planning, these are highly important. We need to determine sometimes that if there's a difference between the workspace and the configuration space. If that's the case, you should be careful about. Otherwise, you may collide with the obstacles. If your robot is a very little one, a thin one, a point robot, then the workspace and the configuration space will be exactly the same. So let's have a look at the details now. In the workspace, actually, by workspace, we mean the physical space, the physical environment. Our robot is moving in any direction. And in this environment, obviously, we have some obstacles. As you see here, this sad S is defining the obstacles. We have T number of obstacles, P1, P2, up to PT. And for the configuration space, actually, we need to define the configuration of our robot. How we can do this definition? We can state that our robot will be at this coordinate, and its rotation, if it has rotational capabilities, you need to define the angle of it. And these parameters will be representing the configuration space, or sometimes we name it as parameter space. Here we have an example, for instance. If your robot is only moving in X and Y directions, then that means it's a translational robot. And here you see you can define the position or the orientation of your robot by two parameters, X and Y, which means that your robot will be located at X and Y, and we represent it by simply R of X and Y. This is the example. Reference point we have at the origin 0, 0, and then once you give the command R of 6 and 4, then that means you will be translating your robot to this position. Obviously, we don't have any rotation. But now let's say that we have rotation, another extra degree of freedom. So we need to define this with another parameter. For that purpose, we will be using the letter phi, and that is the angle with respect to the horizontal axis, and it's actually defined in counterclockwise direction. So right now, in addition to X and Y, we have an extra parameter phi. This is the angle of our robot with respect to horizontal axis, and as I said, it's in the counterclockwise direction. This is the same example we have, just in addition to X and Y, we have now angle parameter. Initially at the reference point it is 0, but now once it moves to 6 and 4, as you see here, its angle phi is 45 degrees. So we need to rotate our robot, and you see it is measured with respect to the horizontal axis in counterclockwise direction. And I mentioned that these are actually, once you add another parameter, then that means you're adding a degree of freedom to your robot. In our example, we have three parameters, X, Y, and phi, which means that our robot has 3 degrees of freedom. It can move in X, move in Y, and rotate around its center. And these are the configuration space, actually, or sometimes it's also named as parameter space, and we represent them as C of R, the configuration space of our robot R. And in the configuration space, actually a point in your configuration space should be corresponding to a placement in the workspace. and this is the placement of our robot. So if you have a point P, let's say in the configuration space, but this, in order to define this point, you need to have X and Y, and sometimes if you have a rotational capability, then you need to also define the angle of your orientation. And this point P, or this definition in the configuration space, should be corresponding to an placement in the workspace, and this is represented as R of P. And these are the same issues I mentioned. So with the help of the parameters you set in the configuration space, our robot actually will be moving in the workspace according to these values you define in the configuration space. And if the robot is a very small and a point one, then anything actually represented in the configuration space will be valid in the workspace. This is a very simple example, so it will exactly be the same. But if you have, let's say, a polygonal robot, then in order to eliminate any collision issues, you need to be careful. For instance, you need to restrict your configuration space. Some parameters may not be valid. For instance, at some point you may not be able to rotate your robot to 90 degrees. You may need to, let's say, limit it to 45 degrees. So not all the points all in the configuration space are always possible. We have sometimes forbidden spaces, and these are named as actually forbidden space, and we represent them as C forbidden of our robot R due to the set of obstacles in the environment. So this is important. We need to define, we need to give a set of obstacles, and as you know, we represent them as with a letter S. Any questions, guys, up to now? And so we have forbidden space, and if you subtract this forbidden space from your whole available space, then you will obtain the free space in which you can easily move. You can set any parameters in this free space. So it means that the parameters which are valid in this free space will have no problem. Well, if you provide these parameters to your workspace, then there will be no collision between the robot and the obstacles in the environment. So during the motion, the physical motion, we should be always using free configuration space. So if you have a collision-free path, then that means it will be mapping actually a kind of a curve in our free space. So you see, we have workspace here and configuration space. In the workspace, we only have, you see, these obstacles. The dark gray ones are the obstacles, and this is our robot. It has no rotational capabilities. It has only translational motions. With the help of them, it moves, it follows such a path and reaches the destination point. And if you look at the configuration space, it's not exactly the same with the workspace. In addition to the dark regions, dark gray regions, we have light gray regions. And you see that our robot, or the center of our robot, shouldn't be touching these light gray regions or the dark gray regions. Otherwise, there will be collision in the workspace. And this is exactly representing the configuration space. So the parameters you are using to represent the motion, the placement of your robot in the workspace should be in this white region. But if you're, for instance, the center of your robot is in this light gray region, then that means your robot going to collide with this obstacle at the center. But if your robot is a point robot, then we will not have these light gray regions. This configuration space will exactly be the same with the workspace. But this is only valid for point type of robots. Any questions, guys? So this is the thing I mentioned. The reference point, the center point will be the point itself, so we don't need to worry about the difference between the configuration space and the workspaces. So now how we are going to determine the path for a given problem. So before constructing the path, we need to construct the free space in which actually our robot can move freely. So this is the first thing we need to do. And for that purpose, you need to have a special data structure which should be representing your free space. And after you got this data structure which is representing free space, we can work on the values inside your data structure and try to complete a path between the start and the final positions. And we will be obviously not using an infinite area. We will be restricting our region with the help of a bounding box. We represent it with the letter B, and obviously our configuration space, free configuration space, should be just inside the bounding box B. It shouldn't be covering the regions outside the bounding box B. And if you have B, the bounding box, then we can simply represent our free configuration space by this simple equation. This free space equal to the bounding box minus or subtraction, we take the difference of it with the union of all the obstacles in the environment. So the rest is giving us the free space our robot can move in any of these points in the free space. This is the example, our bounding box, our free space, as you see. Since we are using a point robot, we don't have, let's say, light gray regions around the obstacles. We don't have such an issue here. The configuration space is exactly equal to the work space. And you see that this free space is a disconnected region. And to determine actually the free space, we'll be using a special type of mapping, and this is called as trapezoidal map. We will be dividing the free space into smaller trapezoids, and these trapezoids will be in sum, will be representing the whole free configuration spaces. And how we do it, it's not complicated. We simply draw actually edges from the segment endpoint. So this is one segment, another segment of the, let's say, polygon. What we do, we draw vertical lines, 2 vertical lines from each endpoint. Another one. And we stop it once you come up with an edge, okay? This is it. Here, another one. I stop when I see a boundary of an obstacle or the bounding box. Then we have another one here. Another one here. Another one. I think we are all done, right? We don't have any missing edges. But now the thing is that since some of these edges are inside obstacles, we don't need to use them. You can reuse them. They're not actually belonging to the trapezoidal map we are looking for. This trapezoidal map will be representing our free configuration space. So we have one here, for instance, another one here, third one, fourth one, fifth one, sixth, seventh, 8, 9, let's say 10, 11. Here we have the 12th one. This is 13 and 14. So you see, we represent this configuration space by using 14 trapezoids. And the whole is called as trapezoidal map, and we will be using this map to determine any, let's say, path between different starting and ending points. Any questions, guys, we have about this map construction?
Hocam, is this work with convex regions?
The obstacles are usually, yes, we prefer to use convex obstacles. Otherwise, things might be quite complicated and your algorithm may fail. And if you're, let's say, let me use another color. If your obstacle is not convex, then what you need to do, you need to obtain a convex hull of it. Let's say that you have an kind of a weird obstacle, okay? And what you need to do first, obtain a convex hull of this blue shape so that the algorithm will work much better in a faster manner. So this is the first thing actually I forgot to mention. You need to do, you should be working with convex shapes. Any other questions? Okay, then let's go on. Let's have a look at the time complexity of this construction of the trapezoidal map. It is written here that it will take linear time, linear expected time. Actually, this is described in chapter 6. This is a main algorithm. I'm not going to discuss the details. We will take it as granted that the construction of this trapezoidal map will take linear expected time. And you see the algorithm, the main algorithm is not complicated, but at the center of this algorithm is calling another function, which is much more time consuming. So what is the input? The obstacles, the only obstacles, and maybe sometimes you need to provide also the bounding box. Otherwise, it will have some infinite edges, half infinite edges. And then the output will be obviously the free configuration space for our point robot. Since it's point robot, we don't need to provide the size or anything about the robot. It's assumed that the robot is a point one. And you see we have some kind of an input for the edges, and then call this function. This function will be obtaining the trapezoids, and then you need to remove the actually trapezoids inside the polygons, and the rest will be representing our desired trapezoidal map. This is the illustration of what we have done actually. And I assume that these points were not aligned, but in this example, you see that they're aligned, so we don't have the 12, as far as I remember, it was a 12, say, trapezoid. Instead of, we have a much simpler version, and this is nicer. So you draw vertical edges from each endpoint, and then simply eliminate the ones which are inside the obstacles. It's very simple. And this lemma, this first lemma is about computation of the trapezoidal map. The same things we discussed. It says that the trapezoidal map can be obtained in linear expected time. And for the rest of our chapter problem, we will be defining the trapezoidal map as T of configuration space, free configuration space. So that once you say T, then it means we are referring to the trapezoidal map of that given space, of the given, let's say, obstacles and the bounding box. So now the question is how we're going to use this free trapezoidal map to determine the motion path of our robot from the starting point P start and the goal point P goal. So that's the question, how we are going to obtain this final path between these 2 points. You may have 2 cases. In the first case, assume that this is the kind of trapezoid you have. Your starting point and the goal point might be in the same trapezoid. If that's the case, things are much simpler. You can simply draw a line in between, and that is the result of your computation in just a single, let's say, operation statement. You can determine this final path between the start and the end points. But if they are not in the same trapezoid, then things are a bit more complicated than this case. In such cases, we need to obtain a kind of an graph. We'll discuss this graph, and once we have that graph, you can work on the motion paths. And in such cases, obviously, our robot will be making some left turns, right turns. We'll maybe going through some obstacles and trying to reach to the final position. So for that purpose, we need to construct a kind of a roadmap by using our trapezoidal map. Once you have the roadmap, then you can work on this data structure to determine the final path of your robot, which is moving from, again, start point to the goal point. And this graph will be named as G road. This is the graph of our roadmap. Here you see an example. Let me describe how do we construct it. Now I will be assuming that this trapezoidal map has already been constructed. Then later what we do, things are not complicated. We find the centers of all these trapezoids. So what do you, how can we determine the center of this trapezoid? An idea? A very simple one. No idea? Average, Talha says, other ideas? What about drawing the diagonals and then taking the intersection? This is the simplest way you can do. You can draw the diagonals, and then the intersection of the diagonals will be giving you the center point for that trapezoidal. So we need to define all these centers, and then later what we are doing, we will be putting some nodes, other nodes into the middle points of the edges. So this is one edge here in the trapezoidal map. Put one, another center point, other center point. So it's not complicated. So this is a center node, and we need to, in the second stage, we need to put nodes onto the centers of the edges. This one here, this one here. So this is the second stage. And then in the third stage, things are not complicated once again. We draw edges from the central nodes to the nodes on the boundaries. Another one here, from center to the node on the boundary, from center to the node on the other boundary. So this is how we draw the lines. Draw another one here. So if you work on this graph, you will obtain this dashed line, and this dashed lines are actually representing the graph of your roadmap. And we are using this part to represent the graph in our, let's say, explanations. And after you got it, then you can determine the motion path by using this data structure. but we will come to that in a moment. Any questions, guys, about how we do the construction of the roadmap? As you see, this is a connected graph. So what do you think? What does it look like? The overall graph. So what does it look like? An idea about the things? Actually, it's very similar to, yes, it's very similar to Jean-Marc Voronoi says. If you think about these obstacles as the Voronoi sides, but obviously these are kind of polygonals, not points. But you can roughly say that this is the Voronoi kind of diagram of the obstacles. So in summary, if your obstacles are very small points, then you can simply draw the Voronoi diagram of it, and you will obtain the graph which is required for your robot motion planning. But again, if you look at it, it's roughly similar to Voronoi diagrams. Do you remember the rule about Voronoi diagrams? At each vertex, we have degree of 3. So you send vertex. This is, let's say, first cell, second cell, and the third cell. So we have a vertex here, and as you see, it has a degree of 3. Another vertex here. Again, it says degree is 3. Another vertex, and exactly the degree is equal to 3. So you can say that they are in general positions, and the degree of the vertices in this Voronoi diagram all has 3 edges at the vertices. So now let's make use of this graph to construct, let's say, path between the start and the final points. These are the same things I mentioned in the previous slide, so I'm not repeating these. So you may have arcs, but to make it simpler, I have drawn simple lines in between the nodes. But in order to make a kind of a smooth, let's say, path, instead of arcs, straight lines, you may use arcs. It's up to you. But since our robot is capable of performing translational motions, that's why we prefer to use lines, straight lines in this roadmap. So the roadmap actually can be completed in linear time. Since we are simply making use of the data structure of the trapezoidal map, we are assuming that this is given, this is the input, and once we have this information, then you can easily determine this roadmap. Since for each, let's say, trapezoidal, we will be putting some nodes at the center, and again, for each edges of the trapezoids, we are putting another nodes at the middle of these edges. So it depends on the number of trapezoids we have. So we can simply say that the graph itself can be completed in linear time. Now we are going to make use of this roadmap to determine a motion plan for a given point robot. So the first thing is actually to determine the starting trapezoids and the ending trapezoids. How we do that? For instance, this might be the starting point. Starting point. And assume that this is the end point or the goal point, destination point. And then what we do first, we first determine the starting trapezoid and the goal trapezoid. So the trapezoid here is actually the starting trapezoid, and the one here is the goal trapezoid. So this is the first thing, and we are now done with that. We can jump to the second step. So again, as in the case of initial discussions, we said that if the start and end points are in the same trapezoid, then you can simply have an edge connecting these points and you will be done. But if they are not in the same trapezoid, then you need to construct a path between these points. So if they are not in the same trapezoid, what we do as a second step, we have a line, we actually draw a line between the start point to the center of that trapezoid. So this is our starting trapezoid, and our starting point is not exactly the center of this trapezoid. So what we do, we connect this starting point to the center. This will be our first line, first motion. And then we do the same for the final destination or final trapezoid. This is the goal trapezoid. This is our goal point. But as you see, it's not at the center of this trapezoid. So we need to make a motion between the center of our last trapezoid and the goal point. So this is the last step of our motion. So we can say that it's the end step of our overall motion. And in between now, we need to define a path between this point, the center of the starting trapezoid, and the center of the goal trapezoid. So once you determine this path, then you will be done. What you're going to do next, you can add this first line to the beginning and add this last line to your motion path. And for the intermediate region, for these regions, motions, you need to obviously make use of this roadmap. This is a part of our graph G road. And in that data structure, you need to kind of make a breadth first search. It's not depth first search, but the breadth first search is preferred here. We need to use as much as, let's say, nodes in the same level, and then go into deeper nodes. So this is how we do find the path. Starting from here, we have two options. It doesn't matter. You can also use this one, but it will be more complicated than the above one. So we go here, we don't have any other options. So once you come here, you will realize that if you go in below, it will be impossible to reach it in, let's say, 5 steps. But if you follow the left route, then you can reach your destination in 2 steps. But in order to do that, you need to have an actually special data structure representing your graph. You may have such a data structure, for instance, you know all the connections. So once you have the special data structure, then you can work on it and determine the path between the center and the other center in the goal trapezoids. Any questions, guys? So let's have a look at the pseudocode, not complicated. What do we need to provide? We need to provide a trapezoidal map of our free configuration space. We need to provide the graph of our roadmap, starting point, and destination point. And then the output of this function, the compute path function, is the path from P start to P goal. And obviously, we will determine it if there is such a path. If it's impossible, then we will say that the function will tell you that this is not possible. We don't have a path between the start and the goal points. So now, as you see, what we do as a first step, we determine the starting trapezoid, which is containing the starting point, and we need to also determine the final trapezoid or the goal trapezoid, which is containing the goal point. So initially we check, although it's written here in a single statement, it may not be that easier if these starting trapezoids are not existing, then you can simply report that we don't have such an, let's say, path between the start and the end points. So this is broken, that the pseudocode is broken here. If you cannot find the starting and the goal trapezoids. But if you find them, Then what we do, we actually have a kind of a start and the goal points. We draw simple lines in between the center node of these starting and the goal trapezoids, and then the rest is done here. The most complicated part of the algorithm, we complete the paths by using this G roadmap, the graph of our roadmap, which is moving from V start to V goal. And with that, during this computation, we make use of breadth first search. But sometimes, although you have starting and the goal trapezoids, you may not come up with a path. Again, if that's not the case, then you should report that there is no path between the starting and the final destinations. But if there's a path, then you need to report this path, which is consisting of straight lines from P start to V start. If you remember, P start is the given point, and V start is the center of our starting trapezoid. So if you connect all these edges together, then you will report the final motion path for the given point robot. So this one actually here, P start, so we'll be reporting this whole motion. Any questions on this pseudocodes or the fundamentals of the algorithm? So now we have some questions and we will discuss the time complexity of these algorithms. What do you think are the paths we are reporting always collision free if you follow such an algorithm? No idea?
No, it's not, I guess. Because breadth first search is kind of simple algorithm, we have to use much more complex algorithm for searching appropriate paths, such as A star. I don't know.
But what about the ones actually we are reporting? I'm asking about the ones we are reporting. Are they always collision free, or do?
What do you mean by collision reaction? I don't get it.
So we are now using this algorithm and giving the user a kind of a path. And are these paths are always collision free, or maybe are we gonna have a collision between the obstacles and the robot? It will be collision free since we are making use of the trapezoidal map of our free configuration space. Since it's already satisfied, so we don't need to worry about collisions between the obstacles and the robots. But you are right, the path we found may not be the best one. It may be the longer one, time-consuming one, but at least we come up with a path. We can say that it's always collision-free. But for better algorithms, you may use different approaches like other search algorithms, A star, or maybe you may have a look at it, maybe depth first search. But if you follow the pseudocode we discussed, we always give you a collision-free path. Here you see another example. Since we are making use of trapezoids all the time, the lines will always be inside the same trapezoid, and we know that inside this trapezoid there exists no obstacles. So, and since our robot was a point robot, the kind of point is moving in the trapezoid, so we can say that there will be no collision inside the trapezoids. So that's why we can report that the found paths are always collision free. What about time complexity? We haven't discussed finding a trapezoids. So we have, let's say, a kind of an bounding box. Let me quickly draw some number of trapezoids here. assume that your starting point is here, and then we have another point, the goal point is here. So the question is, and how much time actually you're going to spend to determine the starting trapezoid and the ending trapezoid. It says that it will take logarithmic time. Why do you think is that? Why it's not linear? Why it doesn't depend on the number of trapezoids we have? Why not O of n? It's very similar to binary search. Since we are aware of the coordinates of all these trapezoids, we can simply check them with the coordinates of the given starting point and the ending point. So you can do a kind of a binary search and tell the user the starting and the goal trapezoids. And for the breadth first search, for determining the path, it will take linear time, since let's say G road has in maximum n number of edges. Then in the worst case, you need to actually follow the whole edges. If you have such a case, then the time complexity will be depending on, in the worst case, to the number of edges you have in the roadmap, in the graph representation of your roadmap. So we can say that now, and this is a resulting theorem. We are assuming that the robot is a point robot, and we have some obstacles in the environment represented with S, and the obstacles in total has n number of edges. Okay, if that's the case, then we can pre-process the obstacles we have in the set S in linearistic expected time. This was, if you remember, the first theorem we discussed. We take it as granted, but the rest is not complicated. We can determine the start and the goal positions in, as you remember in the previous slide, in logarithmic time. But the path from the graph can be computed in linear time. So in summary, for this second part, we can say that the path can be computed in linear time. So if you are assuming that this S is pre-processed, you already have this S information, then you can say that the path can be computed in linear time. But if you modify your path, have new obstacles in the environment, then you need to run your function on the obstacles once again. It will take, as you see, expected linearistic time. In the worst cases, it may be quadratic, but we are assuming that it will mostly take linearistic time.